So this talk will be about fully fault-tolerant streaming workflows at scale using Apache Mesos and Spark Streaming. There's going to be a lot to cover, but I'll just keep it brief, very simple. So a little bit about me and my company Sigmoid. So I'm Akhil. I work at Sigmoid as a software developer, primarily focusing on real-time analytics, big data application development, and distributed computing and scaling and performance optimization. So our company is a 2-year-old startup based out of Sunnyvale, CA, and we primarily provide services on top of Apache Spark, Mesos, and all those distributed platforms out there. These are few of our customers. So yeah. So this is the overview of the talk today. So what I will be covering. First, I will just give a brief introduction to Apache Spark, what are the core components of it. And then I will talk a little bit about Spark Streaming. What is Spark Streaming, how it's operated. And then we'll see what is a high availability Mesos cluster, how do you have a high availability Mesos cluster basically. And then I will show how to run a Spark Streaming application on top of a high availability Mesos cluster. And then I will show what is a simple fault tolerant pipeline looks like. And I will also explain how to have a scalable pipeline. So that is going to be around 40 minutes talk, I guess, and then for 10 minutes I can spend on Q&A. Okay. So yeah, Apache Spark. I guess all of you are familiar with Apache Spark. Yeah. Okay. So Apache Spark is basically one of the top-level Apache projects out there on the big data ecosystem. So they all started around in 2009 at UC Berkeley by Matai Saria and a bunch of other people. So first of all, they developed the Spark core engine, which is written purely in Scala. And then in time, they added Spark SQL for querying your structured data, SQL querying. And then added the Spark Streaming platform for real-time stream analytics. And they have MLlib for machine learning, GraphX for graph computing. And then recently, they have added Spark R from the 1.4.0 release. So the core component of Apache Spark is the resilient distributed dataset. So these are called the RDDs. You will come across that term every time you go to the Spark website or whatever resources you are having. So RDDs are basically, what do you mean by a resilient distributed dataset? So resilient means it's a fault-tolerant distributed dataset. So not all the fault-tolerant distributed dataset is an RDD. So what makes an RDD? An RDD are few of the following properties, like RDDs are immutable. So immutable means, as all you know, like once you create an RDD, you won't be able to change the value of it. So RDDs are like immutable. And RDDs are distributed. They are distributed across the machines. And they are lazily evaluated. What does lazily evaluation meaning? Like you will create a pipeline and then nothing gets executed unless you trigger an action over it. So that's a lazily evaluation. So one of the example could be, you can say, in JavaScript, there is a timer operation. Like the timer actually waits for that function to execute till the timeouts. So that's what the lazy evaluation basically means. And then RDDs are type inferred. So one of the best feature about RDDs are like they're type inferred. You don't have to specifically stick to a type for an RDD. Your RDD can be an integer, your RDD can be a string, or your RDD can be a customized encrypted type also. So those are like, the compiler is smartly figure that out, the type of the RDD. And RDDs are cacheable. You can basically bring up the entire data into the memory of your Spark cluster. And so at the bottom, you can see RDD1, RDD2, and RDD3. This is the lineage of an RDD. So what a lineage means, like from RDD1, I'm creating RDD2, and from RDD2, I'm creating RDD3. So at any point, if RDD3 is lost or corrupted or for some reason is down or something, and then Spark can smartly generate the RDD3 from the RDD2, which means I don't have to recompute the entire process from RDD1 itself. That is one of the advantage of Spark. Now let's move to why Spark Streaming. So many of the big data applications these days requires to process large amount of stream data in near real time. Like these are the generalized category of them. If you are like the monitoring systems are like you have a website and you want to monitor how many visits I am getting from a particular country or how many people are flooding my website. So those kind of actions comes under the monitoring system. And we have alert system in the banking industry. You might want to find the fraudulent transaction as soon as possible before it happens. So at that place also you can use some machine learning and then the Spark streaming combination to detect the fraudulent transactions. And we have computing system like more like they are ad monetization system. Like you go to Google and then you type something, okay, bird nest or something, and then it will show up some sort of ads on that left side. Like they are like real-time analytics. Now, what is Spark Streaming? So Spark Streaming is a platform which can absorb data from Kafka, Flume, HDFS, 0MQ, Twitter, or even from your custom data sources. Like you can have a custom data source to get data into Spark Streaming. And once data is in the Spark Streaming, you can do some analytics over the data, or you can do some transformation over the data, and then you can dump it to your HDFS or the databases, or you can even power your dashboards with that. Now, Spark Streaming was basically originally developed from the UC Berkeley itself by Tathagata Das. It can scale up to hundreds of nodes. It can achieve second scale latencies. It provides batch level API, like similar to Spark only. Spark Streaming also has a batch level API for implementing complex algorithms. And it can absorb data from Kafka, Flume, 0MQ, Kinesis, and all those. Now let's see how it's operated. So Spark Streaming basically runs a streaming computation as a series of very small deterministic batch jobs, which means your live data stream is divided into batches of X seconds, and each batches of X second data is treated as an RDD, and Spark uses the RDD operations to do the computation over it. And then once the computation is done, the results of these process RDDs are returned back in batches. So that's like live stream processing, not like real time, like mostly real time, close to real time, you could say. Now let's see what is a simple streaming pipeline. So I hope everybody is familiar with Kafka here. If not, Kafka is like a message push and pull kind of push-ups, you could say. So it's a distributed message passing system. So I will have a Kafka server, and I have a Spark Streaming application which absorbs data from my Kafka server, do some computation, dump the data back to my storage or my database. So this is a simple streaming application. So with this application, there could be a lot of problems that you will face when you put this in a production environment. So what possibly goes wrong is like everything goes wrong in this thing when you put that in production. One of the reasons is like these are the point of failures available. So one is the Kafka server itself. If the Kafka server is down, your streaming pipeline is basically blocked. There is no point running it. Similarly, if you're running on a single machine with the Spark Streaming, so if the master machine is down, so your entire streaming workflow is down. So you won't be able to use it any further. Similarly for the HDFS also. So the HDFS and then the Kafka itself provides high availability. By default, you can just configure it to configure it. So on this talk, we'll just focus more on the Mesos, how to run this stuff. So this is a high availability Mesos cluster. This is how the high availability Mesos cluster looks like. So in the Mesos cluster, you will have a set of masters. So at one point, there will be only a leader who will be the acting master, like that will be the real master at any point of time. And there will be standby masters. So in a development environment, is preferably we usually set to 3 masters and multiple slaves. So why 3 masters? Like that's like a standard number, 3. Like in HDFS also, like you replicate your data 3 times. That's like a magic number 3. So in production environment, we prefer 5 masters as a backup. So at any point, there will be a leader who will be the master who will coordinate everything. And at any point of time, if the leader goes down, one of the standby master will become the leader and then pick it up from there. So whenever you submit a job to Mesos, those are called frameworks. So here my Spark Streaming job is my framework, which will have a driver program and a scheduler. So the driver program will request for resources to the Mesos. Those are called offers. So offers are the resource allocation requests, and then the master will schedule the job on the slaves. So these slaves will be like executing the Spark. These slaves will be a Spark executor running your job for you. Now let's see how you will submit a Spark Streaming over a high availability Mesos cluster. So to use Mesos from Spark, so first of all, what you will do is you will go to the Spark website, you will download the Spark binary package for your Hadoop version, and then you will put that in your HDFS or a HTTP or on your S3 server where it is accessible by Mesos. So And then you will require a driver program which will connect to this Mesos and then tell the Mesos that, okay, I have this executor at this place. You will have to use this executor to run my job. So that's how you submit a job. So to tell the Mesos from the driver program, you will have to use this configuration. This is one way of doing that. You can also use a Spark submit for that, but Spark submit underneath uses the same configuration. So you will create a Spark configuration. You will set the master to the master URL. There is like 3 masters over there because it's a high availability cluster. So you'll put like mesos // then the zookeeper URLs, and then the /mesos at the end. So and you will set application name. These 2 are necessary. No, these 2 and then the 3rd and then 4th. All of them are necessary, you could say. Yeah. And then you will set the executor URI, which is the one that I downloaded and put in my HDFS. And while submitting a Spark job, you can specify I have to submit in coarse-grained or in fine-grained mode. So there are 2 modes of submitting an application to a Mesos cluster. One is the coarse-grained mode, and another is a fine-grained mode. So here I will be submitting in a coarse-grained mode. So the difference between coarse-grained and fine-grained is that in coarse-grained mode, you can actually specify your resources. You are basically statically partitioning the resources. Like you will say, okay, my job always requires 30 cores and then 10 gigabyte of memory. So if I set the Mesos coarse-grained to false, which means it will fall into fine-grained mode, that means Mesos will allocate the resources accordingly. You can have multiple applications running side by side, utilizing the same resources, basically sharing the resources. So when you have a streaming application or you don't want to have, you want to run a low latency application, the preferred mode is like coarse-grained mode. And with this configuration, I'll create a Spark context, and then I can create a streaming context, and then use this streaming context to build my pipeline. And let's see how Spark Streaming fault tolerant looks like. So in a Spark job or any distributed job, there are like 3 kind of failures commonly. Like one is the worker node failures, another is the program failure itself, and then another is the receiver failure in the case of Spark Streaming. So Spark and the RDD abstraction is designed to seamlessly work with any failures for your worker. So if your worker node goes down, the Spark will take care of that. So whatever job is assigned to that worker will be relaunched on another machine, and then Spark will take care of that. So you are safe with that. And in a streaming job, another important thing is the driver failure. The driver program means the user program itself, which you run on the cluster. So whenever a driver program fails, that means your streaming pipeline is broke, which means you may lose some data. You won't be able to produce any output also for some particular time. So to overcome those, Sparse Streaming provides a checkpoint mechanism where you can just checkpoint your application state into your HDFS or a fault-tolerant file system. And then next time when you restart the application, it will go to the checkpoint directory and then take it up from there. And similarly for receiver failure. So receivers are like, whenever you have a streaming application, there will be a receiver who will receive the data from the data source. So this receiver can also go down. So in that case, the receiver failures are handled by the write-ahead logs by Spark. So write-ahead logs are like, in HBase also you have these write-ahead logs. Like what they will do, they will keep a copy of the data in the disk itself, so it will stay there. So next time, for some reason it fails, then it will go to the disk and then read the data. So you can see the picture below. What the picture means is like the first picture. The blue line says the input stream, which means I'm receiving data from any data source. So the receiver receives data from the data source. And normally what it does is, without the write-ahead logs and all, it just receives the data, it brings the data into memory, and then handles the block information to the driver program, and the program goes on from there. So let's just say, without the fault-tolerant file system, my receiver died. In that case, what happens is the data which I fed into the memory will also be gone. So next time I restarted the block, if I look in the block information, there won't be anything because the data is gone, it's in the memory. So to overcome that, there is a write-ahead log mechanism which will write the data into memory and on the disk at the same time. And then it will send the block information to the block manager, and the streaming application itself will checkpoint the computation to a fault-tolerant system. So that is the working model, and then let's just see the restarter model. So let's just say the framework crashed for some time, And the next time when I restart it, that is what happens in the second picture. So it will pick up the data which are yet to compute from the file system itself, which was being written, and then it will load the metadata for those blocks from the file system, which is a fault-tolerant file system. And then it will restart the computation from the point where it broke from the checkpoint directory. So that's how the fault tolerance works in Spark Streaming. Now let's see a simple fault-tolerant streaming infrastructure. So now they have added the Kafka. Now you can run Kafka also within Mesos. So I prepared this slide much earlier. So you can consider this as inside the Mesos itself. So yeah, for a Kafka cluster, you can have multiple nodes. In the case of failures, the Kafka cluster will handle the failures and all. And then we have a Spark Streaming application running out of a high-availability Mesos cluster. Similarly, we will also have the HDFS or a database running out of Mesos. So which means Mesos will take care of the failures of the workers or the job failures and all. And then our streaming application is also now fault-tolerant. Now let's see how you scale a pipeline. So scaling the pipeline would be like, so first of all, what you have to do is like, you have to set a goal, like I need to process around 1 million events per second, or whatever number that you want. And then you have to consider the bottlenecks that you are having. So nowadays, all those cloud providers, this will be the minimal machine configuration, like every machine will have at least 1 gigabit per second Ethernet cards, and then they have like minimum of 4 cores. Yeah, people usually prefer 4 cores. Yeah. And there are disk I/O. If you are an SSD, you will get at least around 100 MB per second write speeds, read-write speeds. And with all these configuration, let's just say if I want to process around 600 MB per second, so what I will have to do is like I have to spawn up like 6 slaves, which will each will have 4 cores, and then disk I/O and the network of 100 MB per second. So it will be able to receive and then write the data at 100 MB per second. So that's how you create a scalable pipeline and with the numbers. So also one more thing to consider in the scalable pipeline is the bottleneck. So whatever the distributed computing jobs are, so they all fall under these 3 bottlenecks. Like you will choke the CPU, you will choke the memory, you will choke the disk I/O, or you will choke the network. So for the CPU choking, like usually people, what they will do, if they want to write a program or something, they will just blindly put some libraries without comparing the performance of it. So whenever you are, let's say, parsing a JSON or a text document, you will have to either you don't go and code yourself. You just look for the library which is available there, which gives you better performance, and then you will use those. So this was one of the comparison that I did previously. So I was one time parsing a JSON. That was specifically for a use case, and then I found this Boon JSON parser faster compared to the Jackson one. And then the poor data modeling, which is like if you are doing a computation or if you are doing a processing and you don't want to bring the whole data into memory, but you are operating on very few fields. Let's just say you have a data or CSV data of 100 columns, and you are doing the analytics over like 3 columns. And some people, what they will do, they will just try to bring the entire 100 columns into memory without considering like they only require the 3 columns. So proper data modeling is like whenever you require lesser column, just bring those many columns that you require. And compression and serialization also plays an important role. Like when you use compression, you could use the Snappy or LZO, which gives you faster compression, decompression time, and then less overhead on the CPU. And then serialization, there is like Cryo or the Java serialization. You can use that also. Yeah, thank you. So you can ask some question and answers. Yeah, sure.
Yeah, I have a question regarding when you have a receiver, right? When you receive the incoming input streams, and does the receiver save those data to its local, to its local memory, or it's also at the same time it's can output HDFS?
Yeah, without the write-ahead logs, what happens? That's a good question actually. So without the write-ahead logs, what happens? The receiver receives the data, it feeds into its memory without the write-ahead logs. So with write-ahead logs, what happens? It receives the data into memory. At the same time, it writes into the disk also. So your data is replicated in two places.
So if it's only like say if it's local memory, does that mean when you create RDDs, does that mean that RDD physically only only exists in that particular machine which has a receiver? Because other machines doesn't have this in-memory RDD. You see what I'm saying? So that means if you create only one receiver for the input stream, does that mean that physical RDD only exists in that particular?
Yes, you could say that because the data locality will be referred to that machine itself. So now whenever you do a task, so there will be a single partition over there. So the single partition will be on that single receiver which was running on that machine. So your job will always run on that same machine. If you want to distribute it, you will have to do a repartition. So all the data will spawn across machines.
So even though I could have many executors for the particular Spark,
Yeah.
But actually when I do Spark Streaming, that only that the only server which has this receiver can do jobs. You can execute this RDDs. You see what I'm saying?
No.
Oh, sorry.
Can you come again?
So let's say if this I have like 100 machines for this we set up
Job,
100 machines for this Spark, right? But I only have one receiver. Okay, if that's the case, this Spark Streaming cannot leverage all 100 machines.
No, it will always run on that single machine.
On only single machine.
Yes, you will have to do a repartition basically.
Okay, I see.
Yeah.
I noticed Kafka was external to Mesos. Have you considered bringing that into Mesos with the new framework support? Or
Which one?
the diagram that you had in Kafka outside of Mesos?
This one?
Yeah. Have
Yeah.
you considered bringing that into Mesos with the new framework support? Or
Yeah, now they have added support for Kafka also. There is another talk today itself, I guess. You can bring Kafka inside Mesos itself as a framework now. Yeah.
Is it always a requirement for running single Spark executive per node? Because you could potentially have
Multiple
Spark
executors, yes.
Executors. Which one is preferred? Like
So if your machine is comparatively smaller, let's just say your machine is less than like 100 GB of memory and all. In that case, you can have one executor. So let's just say you have a bigger machine, like more than 100 GB memory or 200 GB memory, the physical memory, and then more than like 64 cores. In that case, you can have multiple executors running, because the JVM won't be able to handle that much of memory at once.
so, I guess what's the guidance there? Like, what's the sizing guidance?
As of now, I'm not much familiar with the sizing guidelines over there, but it's preferably like if your machine is higher, you should better have like 3 times, like divide by 3, yeah, resource by 3, you can do that, 2 to 3 times, yes. Yeah.
Similar to the Kafka question, do you recommend using Spark, deploying it with Marathon on the Mesos, or having it run alongside something?
Yeah, sometimes we do run it on top of Marathon, yes.
And how would you prevent Spark from overrunning your Mesos cluster? So if you're just scheduling Docker containers alongside of it, do you recommend having like one Mesos cluster just for Spark? Or
No, we run application side by side.
Okay.
Yeah.
Do you ever run into a case where Spark's taking over like 50% of the cluster?
Yes, that happens when you put that in fine-grained mode. When you are running in a coarse-grained mode, you can actually set the number of resources that you want. You can partition the resources for your Spark job.
So like at the beginning, the best thing to do is just
Yes.
make sure.
Yeah, I can show you that actually. Yeah, like this. Here I am specifying the resources. So my job will always occupy 30 cores and then 10 GB of memory. Yeah.
You had information about compression. Encrypting the data,
Encrypting the data.
either coming either in Kafka or within Spark Streaming itself.
As of now, with Spark, there is no encryption of the data. But you can implement encryption. Like you can implement the Java-based encryption, like when you have a RDD, when you bring the data into Spark, and then you can have a separate stage for encrypting the data. So next time, once the data goes to the encryption state, so everything will have encrypted data. Anything else? Okay. Thanks a lot, guys.